Ah, sorry, didn't see you there. You heard of black holes, right? This is Messier 87, first ever black hole image. And she looks exactly as I theorized. Some say Messier 87 is very big, but what's actually big is her accretion disk. That's the matter orbiting around her. And right inside the accretion disk is her event horizon. The point where light can't escape the black hole's gravitational pull? Technically, but I don't like the wording. It implies light is being pulled so hard it stops, but light can't stop. It's always traveling at the same speed. Here, I'll prove it to you.
Here's a simple two-dimensional universe. We'll draw straight grid lines to represent the fabric of space-time. Now, watch what happens when we add a planet. Space deformed around it. It sort of looks like a bowl, but it doesn't actually need to curve down. Actually, it's better if it doesn't, because this model of gravity is missing the dimension of time. See how space-time contracts? That's gravity in action. For a bigger planet, space distorts faster. For Earth, it distorts at exactly 9.8 meters per second.
But why can it contract like that forever? Why doesn't the Earth collapse in on itself? Why not? We know the universe is expanding. There's no reason it couldn't shrink, too. After all, the grid lines we've drawn to illustrate the warping are arbitrary. You can imagine them like strings pulled taut across space. Nothing is touching them, yet they still fall down. Why? They can't help it. What else is there to do? You see now that gravity is not a force. It doesn't push or pull things. It's more like running against a treadmill, moving in the opposite direction. When you stand still, the treadmill seems to move you backwards, but it isn't really pulling against you. Even with nothing on it, the treadmill would move all the same. What about black holes? What makes them so special that light can't escape their gravity? Aha! Now we get to my favorite part. For a black hole, so much mass is packed so tightly that it warps space-time faster than the speed of light, so severely that light can't move forwards through space. Doesn't that mean it stopped? That depends on your definition of stopped.
Here, it's useful to bring back our bowl model of gravity. Let's imagine the vertical axis as time for the sake of the metaphor. Here's our planet. When light moves through the field, it seems to slow slightly because some of its speed is converted into the temporal dimension. Here is Messier 87. Past the event horizon, space-time is distorted infinitely. When light enters, all of its speed is vertical. Despite being the fastest thing in the universe, light stays perfectly still in space, aging at nearly 300,000 meters per second.
So, that's your introduction to general relativity. What did you need again? I just wanted to borrow a pen. Still, that's amazing. I mean, this theory explains everything perfectly. If only it did.